Hey, students. I just got a request to kind of go through number 48 here. So let me work through it. It is, well, maybe I should just read it, but I printed it up here in the hard copy. It says, find the total Coulomb force on charge Q. So Q's here in the middle of this square. Given that Q is 1 microcoulomb, QA is 2 microcoulombs, QB is -3 microcoulombs, C is -4 microcoulombs, and D is 1 microcoulombs. Now, if you kind of remember the whole setup of this chapter, is Coulomb's law says, okay, you know, what are the forces between all of these? So we learned that there was a force between any two charges as K, Q1, Q2 divided by R squared, where these are the two charges and this is the distance between them. And so in this case, we will have pairs like this. We will have Q interacting with A, Q interacting with B, Q interacting with C, and Q interacting with D. So we should have 4 of these. In fact, maybe I'll kind of draw the forces in red. Let's see. Here we have 2 positives, and so the force would be pushing away, kind of towards this corner. And then looking over here at D, since it is also positive, it'd be pushing it away. I'll draw a little smaller arrowhead because it is only 1 microcoulomb, and this one is 2 microcoulombs. And likewise, we can play the same game here, that the positive in the center and QB, which is a negative, would be attracting it. So it looks something like this. And then the 4 and the 1 would be attracting, and it'd be, I guess, a little stronger than the 3. So I'll draw it as an attraction towards C, but with a bigger arrowhead. Okay, so in order to solve for what they ask, let's see, total force, is we've got to then add up these 4 forces. And if you remember from last semester when we did forces and their components, we said, okay, we got to take the x component of each of them. And so technically I need to take the x component of number 1, add it to the x component of number 2, add it to the x component of number 3, and add it to the x component of number 4. Now, I say technically, and the same thing for y, because I might notice something that might save me a little bit of work, and so I think I will here, that when you're working with vectors that are in the same direction or even anti-direction, they're a little easier to work with. So in other words, the A and the C are opposite of each other. And so it would be pretty easy just to take the value of D and subtract A, or excuse me, the other way around. This is A. Value of A and subtract the D to get the result of just those 2. And then I could do the same thing with the C and the B. Let's see, this is the C1, which is a little smaller than that one. And so it looks like I would have a net from these 2 kind of pointing down here, and a net from these 2 pointing down. And then I can do my x and y. So I think I'll take that approach. But this isn't too bad either. It's just very mechanical, and it'll get us there. Now I question if I should go this kind of unique way, because I have a feeling most of you might just be thinking of this. And this is the, well, I'll tell you what, since doing components is required later on anyways, let me take advantage of what It's probably not a shortcut. I kind of thought it might be at first, but I now that I think more deeply, I don't think it is here. So let me do this. Let's just look at the magnitude of the force, and I'll call it these two. Let's call it A, D. You know, what is A and D together? Because if I look at the magnitude of just A, I get Coulomb's constant, distance squared. And for A, the two charges are a 2 and a 1 microcoulombs. So this would be a 2 microcoulombs and a 1 microcoulombs. And maybe just to save some calculator work, let me just say that, okay, the K I'm going to leave alone. The 2 times a 1 I'll put in. I won't even bother to put in the micro yet, times 10 to the minus 6. And also downstairs, the separation is half the diagonal of it. So let me call it R1/2 squared, meaning it's the length of whatever half the diameter is. See, the reason I thought that might be kind of useful, just to save me a lot of time, given how much steps I have to do here, when I write out the force for D, almost everything's the same except for the charge. There'd be a 1 and a 1 instead of a 1 and a 2, but the distance is the same and Coulomb's constant is the same. So keeping that in mind and looking at all this, this would just come out to be this value, where instead of getting a 2 times a 1, I have a 1 times a 1. And since I want to know the magnitude of A and D, noting that the force from A, kind of a down to the right, is bigger than the force from D, which is up and to the left, I would subtract these two. I would take the force from A and I would subtract that one. So when I subtract these two, we're looking at just 1, and then we have microcoulombs squared, and then the distance of half the diameter. So that would be my so-called shortcut. But like I said, I'm not really sure this is going to be much of a shortcut. And let's kind of do that same logic with the magnitude of the force from B and C. So B, C. And again, kind of that same logic here. What is the magnitude of the force from B? And again, it's going to be Coulomb's constant. And so when I look at B, there's going to be a 1 and a 3. And it's going to be kind of up to the right. I won't worry about the negative. I'll keep in mind what direction it is. I'll use the fact that these are opposite charges to remind me that it's up and to the right. But I'm doing the magnitude, so I'm not going to have a negative value. My point is, if I follow the same pattern that I did up here, a lot of things would be the same, like Coulomb's constant and the microcoulombs and the half the diameter of this square. So there's a 3 there. And then, if I kind of do this same logic for the force from D, again, D is a negative and the center one is positive, so it's an attraction, and so it's down and left. But it would come out to be Coulomb's constant and 4. So a little bigger. but everything's the same. And like we did up here, this would be the nice thing about just kind of grouping those two together, is that then this would be only a difference of 1. Okay, and so let me take these two forces and put them together. Okay, maybe I better start numbering these. These might get kind of long here, but I don't think we have too much more to go. So again, the goal is to add all 4, but like I said, all 4 would now just be these 2, because this is A and D, and this is B and C. And maybe I'll draw a little free body diagram before I go too much further to kind of recap of what I've done so far. And so A and D, okay, with A being the stronger one and being to the right and down, means that AD is like that. Force AD. And likewise, the attraction of the C is greater than the attraction of the B, again, by this BC amount, again, same as AD, notice. And so this is left and down. And so left and down. And then you can hopefully see that if you look at these components, this AB, oh, maybe I should label this one. What was that again? BC. I'm hoping you can see that since they're the same magnitude and they're the same angle, I guess I don't know if I said much about the angle, but it would be, down at 45 degrees, and this would be down at 45 degrees. They're along the diagonal of the square. This would be going to the right and down, and this would be going to the left and down. But my point is that the x component, this one going to the right and this one going to the left, are equal and opposite. And so now, if I say look at the x component, I'm going to get just a 0. And so that was kind of nice about this shortcut, if you will. But like I said back here on this first page, if you just did all of these, you would find that, you would have 2 positives, 2 negatives, and when you put them all together, you would get 0. So, again, not sure this is so much better, but I do like how it is very physical and intuition instead of maybe just more mathematical. So technically, we didn't have to actually do components here, and that was nice. But we still have to do them there. But we did save ourselves, I think, a little bit of work. Because notice that this force AB, the down component, is the same as the down component of BC. And so the total down component, and so the y here, and so I'll say Fy total, that's all 4 together, is twice the vertical component of the AB. So in other words, I'm going to take this problem and just look at the vertical component of the AB and then double it, and I get the entire vertical component, which is the entire force, because that one came out to be 0. And so that's why I called it a shortcut. But again, I kind of think if I just blindly plug and chug, I might be done by now. So maybe it's not a shortcut in time, but maybe a shortcut in calculations. All right, so now let me step away from that, and let's finally actually do the calculations. We have a number of the magnitude of AB, which, if you remember back here on page 1, we got this. So Coulomb's constant is 9 times 10 to the 9th when you put your units as newtons and meters squared and coulombs squared. So that's the K. We got the 1, you remember, by putting in the amount of charge. We never did put in the micro, so this would be times 10 to the minus 6 squared and coulombs squared. That's what's meant here by squaring the units microcoulombs. And then, of course, we do see that the coulomb squared is going to cancel off. That's good. And then on the bottom here, this is the diameter cut in half. Now, you might remember a little bit about your 45 right triangles, because they're saying this square is a half a meter. So first thing, notice I'm going to change the 50 centimeters into a meter, and that's because I have Coulomb's constant in meters. Okay. And then if I take this diagonal, the diagonal is the square root of 2 times one of the sides. Okay. And that would be its length. So let me cut that in half in order to get half the diameter. Okay, so the numerator here is the diameter. Cut it in half. And of course, depending on how you want to look at this, 0.5, let me cross it out and write it as another 1/2. So this is actually a root 2 over a 4 for half the diameter. And what I want to know is that half the diameter squared. So when I square this, the top just becomes a 2, and the bottom becomes a 16, and that reduces to 1/8 or 0.125 meters. So I'm going to take advantage of that in this calculation here, 0.125 square meters. Okay, so now I'm going to get the calculator here and put in this number. So 9 exponent 9 for Coulomb's constant times, and 10 to the minus 6 squared becomes 10 to the minus 12. And then, as we said, the distance squared is 0.125. And it looks like I get a force of 0.072 newtons when this is all said and done. Now, I don't just want the magnitude of AB, I want the vertical component. So the vertical component would be this number, and then multiplied by, let's see, if I'm looking at this angle of 45, I want opposite, so I'd multiply it by sine of 45. And using that back up here to finish this problem, I'd have 2 times this number, 0.072 newtons. And the sine of 45, which I guess I could just use my calculator, but it is a root 2 over 2. And I like that just because now the 2's will cancel off. And so to finish this, I will just take this
magnitude and then multiply it by the square root of 2 and come up with 0.102 newtons. And I guess maybe for a grand finale, then the force on that one would be 0 in the x direction, which probably shouldn't write anything then. And then actually I come back. Did they ask for the magnitude or the direction? Find the total Coulomb force. Total. Okay. So the total force then is a negative 0.102 down newtons. All right. Hope that helped. Bye now.